Hi, welcome back to the Cuzzy Sound channel and part 14 in the series all about my Project 12 DIY modular analog synth. In this episode I'm going to be looking at a modification that I've made to the 4046 VCO that's in Project 12 that will hopefully give me an alternative waveform output from the standard square wave that the chip produces in this configuration. What I'm going to be using to do this is a technique I've used before, which uses an RC filter, R standing for resistance, C capacitance, and the filter acts as a sort of integrator. So it receives a square wave signal and then integrates that signal, so it tends to add a slope to it. It's a technique I used when I did the pseudo triangle wave output on the 555 VCO that I used in my Project XII analog synth. So this is what the RC circuit looks like. It's a passive circuit. What you're actually looking at here is two RC filters. The reason for this is that the first resistor capacitor arrangement starts the integration process. What this would actually produce, and this is similar to what I got out of the 555 VCO, what this produces is a kind of a partial triangle wave, which is kind of more a parabolic slope to the leading edge of it. If we then feed the output of that into a second RC filter, we get something which looks a lot closer to an actual triangle wave. We'll have a look at this in a moment. I've got the oscilloscope running. So that's the basic circuit. Ignore the values on this at the moment. I'll talk about values in a moment when we start looking at what the output looks and sounds like. But basically it's a passive circuit. It's very simple. So it's two filters, one following the other, producing a double integration that converts a square wave into something that's pretty close to a triangle wave. For the purposes that I've put this to, what I also wanted to do was buffer the output. So I added an op-amp buffer to the circuit, and with the buffer on it, the circuit looks like this. So as I say, for the time being, don't worry too much about the values that I've used for the resistors and capacitors here, because we'll have a look at what effect using different values of resistors and capacitors can have on the shape and performance of the output. So to do that, let's go over to the bench and have a look at some of the circuits I've been playing around with, and then I'll demonstrate what I finally decided upon as the alternative waveform for my 4046, and set up a little bit of a patch and let you hear what it sounds like in use, because that's why I'm doing this. It's not because I want to test the theory, although I'm learning from testing the theory. I want to be able to play it. I want to actually hear a usable sound, something that I like, and so you'll hear what I came up with at the end. Anyway, I'm rambling now. To the bench. Before we look at modifying the circuit, or the waveform generated by the circuit, what we'll do, we'll just quickly show you what the basic output of the 4046 VCO looks like. I'll shut up because my voice is bouncing the scope. Probably not the tidiest, sharpest looking square wave you've ever seen, but it's a square wave. Right, we'll have a look now at how I've been playing around with modifying that, and we'll start with a reproduction of the circuit that I've done on the breadboard. I'll just explain what we've got going on here. That's the 4046 chip, so that's the VCO. That is a TL072 op amp performing two functions. The first function is to provide a conditioned voltage to inject into the 4046 so that we can actually have a control voltage to change the pitch of the oscillator. And then the other side, because it's a dual op amp, so the other side of it is acting as the buffered output, similar to what you saw in the second of the circuit diagrams that I did. The whole thing is powered by this 9-volt battery here, and then the output from the 4046 is going into this arrangement here. And so what I've got is, it's the two resistors and two capacitors forming the double RC integrator circuit that was in the circuit diagram. In this case I've got two 1K resistors, and the two capacitors are 220 nanofarad. If you remember in the diagram, I got 10 nanofarad, so these are significantly bigger. But this is the value that the 220 nanofarad, if I remember rightly, that was the value I used when I built the passive low-pass filter circuits for my Project XII synth. So let's turn it on and see what happens. Just connect the power. You've got a triangle wheel that's bouncing. I'm going to turn the mic off or down. One of the reasons that the waveform is going up and down is there's background noise. There's a fan background noise in the room, and it's causing a nice kind of almost sine wave oscillation superimposed on the waveform. That's what that wobble is. So if I turn the mic down, you will actually see what just the waveform is, and then I'm going to change the frequency of the waveform so you can see what happens. So what you were getting there is it's the same effect that we got when we did the square to triangle wave conversion on the 555. You drop, as the frequency goes down, the frequency of the oscillator is too slow for the integrator to fully integrate the whole of the square wave, so you get partial integration and then partial square wave. So if I bring it back up, but then if I increase the frequency again so it gets back into the right range to match the capacitance, then you'll see it'll go back to a fairly neat triangle wave. So the kind of clipping of the triangle wave, it went from being a partial triangle, partial integration, partial square, to kind of like a clipped triangle, so it got like a flat top on it. And the higher you go up in the frequency, the more credible a triangle wave it becomes. So, I'm back to where I was when I did the 555. I've got a workable range up to a point, and then after that it starts to break up. Now what I did, I played around with different capacitance values, and the ones that you saw in the circuit diagram are the ones I ended up with, which actually produced something which is a little different to what I was aiming for. I tried a range of capacitor values, but I actually found that by working outside the limits and theory of the RC integration of a square wave into a triangle wave, I ended up with something that was a little bit different to what the original purpose was. But, well, let's go and have a look and have a listen, and you'll see where I got to. Right, just to remind us, there's the original square wave and what it sounds like. Now, if you remember on the circuit diagram, I had 1.8k resistors and 10 nanofarad capacitors. Now I'm going to show you what the waveform looks like when we take the square wave output and pass it through that arrangement. And remember, this is double filtered as well, so there's two RC networks. A real spiky, fizzy output. So there you see, let's take that out. The way I interpret what's happening there is it's related to the frequency of the oscillator has to be matched to the size of the capacitor in order to get the integration, as we've been talking about earlier. What I've done here, because I've got relatively small capacitance, those capacitors would probably produce triangle waves if I was working in the tens of kilohertz frequency range, which for audio is once you get beyond 16k, you're pretty much starting to entertain the dogs. So it's kind of it's outside of the range that we want, but because I pushed it way beyond the range that we would normally be playing with, what I'm actually getting is I'm getting the leading edge of the square wave is being integrated, and then the capacitors have discharged, so you drop down and then you've got this kind of notch before you get the next leading edge of integration. So what I'm actually producing is kind of a spiky pulse waveform output, which is why you get that that real fizzy noise. But I've still got the square wave output, and this is where I found that the fun was really starting. If I get there's a spiky output. If I now start to reintroduce the square wave, so I've got both waveforms operating at the same time. I'm going to step across the camera slightly. I'm going to turn the Baby 8 sequencer on. That was starting to sound really interesting, and that is something that I thought, yes, I can probably play with that now. So I've not ended up with the triangle wave that I was thinking about when I first thought about modifying the output of the 4046, but what I've ended up with is something which I wasn't particularly expecting. It wasn't where I expected to end up, but I like it. I like that I can add that fizz to the warmth of the square wave and get that combined sound, and so I thought, well, okay, I've not ended up where I wanted to be when I first thought I wanted to be when I set off, but I've ended up somewhere interesting that I like, so I've kept it. If you're interested in what the actual circuit board layout looks like for that double integrator with buffered output, then this is the stripboard layout that I built to add to the 4046. Real kind of very simple, straightforward arrangement that you just feed it with the output of the square wave from pin 4, I think it is, on the 4046, and give it its own jack socket output. Okay, well, how can I use this now? Let's set up a little bit of a patch and see how we can do even more sound shaping. I'll talk you through the patch, then we'll play the synth. The key point here is I'm just using the one 4046 VCO, which now has its original square wave output and the spiky notch processed output that we've just been talking about. The square wave output goes into a Vactrol. The Vactrol output from the Vactrol goes into VCF. There's no CV on that VCF, and then the output goes to the mixer. The spiky waveform goes into a Vactrol. Out of the Vactrol it goes into the MS-20 style VCF. The control voltage on the MS-20 VCF is being triggered by a looping envelope, and then the output goes to the mixer. The CV input to the VCO is coming from Baby 8 sequencer, and the gate output from the Baby 8 is going through the gate buffer to provide the gate signal for the two Vactrols. So it's one oscillator, two filters, two Vactrols, one looping envelope, running one sequence on the Baby 8. Right, let's see what that sounds like. And all from one humble 4046 VCO with a couple of resistors and capacitors added to the output, and it opens up a whole new world of creative possibilities. I've shown you the circuit diagrams. You've got the previous videos on how to build the 4046 VCO. You've got this video on how I created the wave shaping. What more do you need? Go on, have a go, build your own.